Okay, so let's talk about end behavior in this one, and then we'll talk about zeros later. Maybe that'll be a third video. So end behavior. So here's the definition, a general definition of a polynomial. So just very generally speaking, what p of x does. When the absolute value of x is large, and so actually it's two questions that might have the same answer or might have opposite answers, might have different answers. So it's basically two questions. What happens when x is a large positive number? That's one way. It's one way for absolute x to be large. And then here x is, so x could be a large positive number. X could be a large negative number. A negative number with whose absolute value is large, like negative 10 billion or something like that. Constants and linear functions are a little bit special. They're not curvy, they're just completely straight. So constants are just strictly horizontal. So let's just do special cases here. And I want to talk about, on the other side of the dry erase board, I want to talk about what happens for degrees that are larger than 1. So we should kind of already be familiar with parabolas, and that kind of should point us in the right direction, but let's just say it once and for all. What is the end behavior of every polynomial? Well, we kind of already know that if n is equal to 0 or undefined, those are the two, it's either the 0 function or a constant. The end behavior is, well, that's what the shape of it is. It's flat. It's either the function is always 5 or the function is always 12. The function is always, the output is always negative 12. Not much to see here. So those are special cases. And then, well, if n is equal to 1, well, there's actually kind of two cases. So p of x could be like 3x plus 1. And then the end behavior is, okay, yeah, sure. It's when x is large, the y values are also large and positive. And then when x is large and negative, the y values are large and negative. So you know that it's that diagonal line. You've already described the end behavior. The other cases will make negative 1/2. So the coefficient is negative. And we kind of know that the coefficient doesn't matter very much. Well, if the slope is 3 on this other one, then relatively speaking, one of them that one would be steeper, and going positive in the positive direction, and then going down as x goes in the negative direction. And this one's kind of the opposite. So this one, g of x, what looks, sorry, these are kind of running together. Let's try to keep them a little bit separate. So constants look flat. Well, if you have a non-zero coefficient on x, and then if that's your highest power of x, then sure, you've got positive slopes or you've got negative slopes. And the end behavior is, yeah, it goes down endlessly, but it's not in any super duper hurry to get there. It's, just at this constant speed, slow and steady, it's going down, endlessly as it goes to the right, and it's going up as it goes to the left. So those should already be kind of familiar. So you might want to stop and spend a few minutes. You might want to think about, what if I have plus or minus x to the 8th? What if I have x to the 12th? Plus or minus that. And what if I add or subtract two different powers of x? You might be able to make some educated guesses, and you might even get them correct, even if you've never done it before, if you think about it for a bit. But we're going to walk through all of that right now, and we're going to say why and how it ends up being what it is. So, all right, so the main principle of end behavior is this leading term test. So kind of the principle here is that when you have a polynomial with, maybe you have not just one term, maybe you have several that are being added and subtracted from each other. All of them are doing things, and they're all kind of important, but what happens, we can sort of, if x is very, very big, we know that the largest power of x is going to be much bigger than all the others. So if I have x plus x squared plus x cubed, well, when x is equal to 10, you'll see very rapidly, what if there's an x to the 7th? What if that's our highest power? Well, wow, that's like, this person's only got 1,000, but that one's got 10 million. If you plug in 100, you'll see very rapidly the largest power of x after a certain point. And no matter what the coefficients are, this one just keeps growing much faster than all the others. And as long as you have a leading term, by definition, that the coefficient is not 0. So that one just eventually wins. You're the champion. Eventually, a lot of interesting stuff can happen in the middle of the graph. But if you plug in a big enough positive x number or a big enough negative x number, then the size of it is going to overwhelmingly be determined eventually by the leading term. So in this example, it's like x to the 7th. So you can go ahead and if you want to, you can go ahead and like the exact shape, the exact order of magnitude, how big it really is, what specific numbers you hit along the way, all of that changes. But in just the broad picture, does it go up or down? You can think of in your head, if you understand these two, and if you understand what the plus or the minus in front accomplish, then that kind of tells that kind of has exact same end behavior, whether it's x to this x squared, or if it's plus or minus x to the 8th, x to the 132nd. So, there are two different cases to consider, because, the exponent, turns out the exponent being even or odd makes a big difference. It's a big deal. And then the coefficient being positive or negative makes a big deal. So there could even be this could be a 5x squared. But what do we need to know? We need to know, is the degree even or odd? Is the coefficient this thing an that's in this context, an refers to the leading coefficient, and is that leading coefficient positive or negative? So if we have n even, let's do a graph of it. So y equals p of x, for example, could be x squared, or it could be 2x squared. Well, I'm going to draw a picture of x squared first, but then let me show you what they actually put in the book. So y equals x squared, that's specific quadratic, is this nice happy parabola that's nice and smooth. If you know that your function is exactly this, well, that's a positive coefficient. And if on the other hand, if there's a minus sign, yeah, well, maybe I should go ahead and I should do, here's 1, here's x equals 2, and 1, 2, 3, 4. Maybe I should have slowed it down and made sure I hit those points exactly. Well, in a minute here, I want to sort of talk about what happens for other functions. So other functions are not quite as well behaved in the middle, but in behavior, what happens on the very outsides, these arrows that are curving up or curving downward, that's going to be the same no matter what the function is. So so if the leading coefficient is positive and the exponent is even, it behaves just like x squared. So the general case is I'm going to erase what happens in the middle, because the reality of what happens in the middle is when everything's up for grabs. X is not super duper huge, so depending on what it depends massively on what are the coefficients, the individual terms, they fight it out. It goes up, it goes down. Maybe it's a 12th degree polynomial, and maybe some of the middle terms have really large coefficients, and it could go whoop, 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 but then eventually the book does this little zigzag thing, but eventually if x is a really big positive number and the coefficient is positive, then it's just up no matter. So you take a big negative number like negative 100. Well, every time you have 2 copies of negative 100, that's a double negative that cancels. And negative x to a large even power, all the negatives cancel, and it's up no matter what. And then the book has a little zigzag in between, because it's like what happens in the middle, that could be super duper interesting. It just really depends. That's a complicated question. Every polynomial has its own unique behavior. We know some things in general about that, but right now the first thing we want to learn is the end behavior, and that is even powers of x eventually accelerate upward if the leading coefficient is positive. So it accelerates upward as you go to the right, and then as you go in the negative direction, you plug in very large negative numbers, that also goes up and up in a way. So same thing with minus x squared. That is a model of what happens for any just the overall in the middle. Could be who knows what. There could be ups and downs. In between. Just really depends on how many middle terms are they, how much do they disagree with each other. It can be a really complicated question, what happens in the middle. What exactly happens for a particular example. So what the book does, it has a sort of zigzag that sort of represents the so minus x squared, or it could be, this could be minus x to the 10th, could be negative x to the 100th, it could be negative 1/12 x to the 10th. We have the coefficient is negative, and I believe I've been using green for the degree in the previous video, so let's do that again. So n is even, n is even, and I think I used red for the, so something like this. So it could be negative 2x squared, it could be negative 7x to the 8th. So one thing you can do is just first of all, you can just sort of try to understand what happens when the leading coefficient is positive. And if the leading coefficient is negative, then it just means that both of them get reversed. You've vertically reflected how the leading term behaves. And the leading term is going to win. So if a positive coefficient does this, negative coefficient does the opposite. So just understand these two first, and then just if the leading coefficient is negative, then both of these are the opposite. So here this could be, I don't know, 4x to the 100th. Well, that one's going to blow up really, really quickly, for sure. But, you know, if P of x is even power with, you know, even degree, and leading coefficient positive, that's all we need to know for the end behavior. There could be other terms that maybe there could be 7x to the 91st. Doesn't matter for the end behavior. In between, lots of things can happen. But we know the end behavior just because we know the leading term test says you get the final word here. All right, so x cubed or y equals x cubed. We're gonna just say in the middle. Maybe it's not exactly like x cubed, but we know that odd powers are like this. That it's like if you take, you know, positive coefficient times x to the 7th. You plug in a negative number, take the 7th power of a negative number. You get double negative, double negative, double negative, and then because it's an odd power, you have another one negative left over. It makes it negative, but it's really big. So it looks like this. So a negative to the 7th equals negative. But you know, you plug in large positive values. Positive to the 7th is equal to positive. And in between, well, maybe there's 3x to the 6th. So in between, they can disagree with each other. Lots of things can happen. But here we are. We got odd degree, positive leading coefficient, and negative leading coefficient means exactly the opposite behavior. So if you're comfortable with this way of thinking, you can sort of figure it out for yourself just by thinking about what happens if I plug in big positive or negative number. If you're not comfortable with that, you can just memorize the test. So it's for reference, it's that there's the page in the book. It's page 228 and page 229. What's your degree? What's your leading coefficient? Positive leading coefficient, even power look like x squared, which it goes up and it goes up. X cubed means it would be it goes down as you go to the left and it goes up as you go to the right. But then if the leading coefficient is negative, it's completely the opposite. So I usually think about what it would be if it were a positive coefficient, and then I just reverse that if the coefficient is negative, and then if it's positive, I just keep it the same. And yeah, there's a lot of connections here. It's kind of like transformations. Multiplying the leading coefficient by a negative number vertically reflects the entire function, which in particular vertically reflects the end behavior. This up becomes a down, this down becomes up. It all kind of holds together like that. This is already, so I've been talking in generalities here. Maybe we should, I'm gonna have to erase no matter what I do. So let's just I think we can do some rapid fire ones up the top. So let's describe the end behavior and just put a few examples on the top, this top part of the board here. Okay, so all right, so let's just let's do this first one. P of x equals 3x squared minus 5x plus x to the 17th minus 1. Well, here's the thing to notice. I didn't explicitly write down a coefficient, but if it's x to the 17th, then that's the same as one copy of x to the 17th. So here's the coefficient. If you remember, the entire expression 1 times x to the 17th is called the leading term. So how does x to the 17th behave? It's positive times an odd power, which means it not only does it go up and down and then up, it kind of accelerates, so it actually bends, gets faster and faster as it goes along. Well, if it were negative, this is not the case that we're in here, but it would do the opposite. So you can sort of start with what would it do if we had a negative coefficient? It would do the opposite, but we don't have to go that far. We just, we know it acts just like x cubed. In the kind of, what does it do in the extreme cases? Let me just to make it more like the book. The book has this very rigid, perfect zigzag that it does. So that's what the book does. All right, so then all right, so here I put square roots not over the entire thing, but just over the coefficient. So be very careful where your square roots begin and end. I just answered part A here. Let's erase it because I need the space again for part B. So, all right, this one's also not in standard form, so just take a minute. A lot of times it will be given in standard form, but you never know. So I'm just being overly cautious. I'm just doing a lot of these like this. Well, here 8 is the highest power of x. This, and that. Okay, so what do we have? X to the 8th, that's an even power of x, so it looks like this. X to the 8th looks like this, but what we have is we have a negative So this is not the final answer because this is just how x to the 8th behaves. Well, what I have is I don't have a positive number times x to the 8th. I have a negative number times x to the 8th. So that's one additional minus sign. Which means that up goes down, this up changes to a down. So it's not this. Well, I don't have to cross it out because this is describing, well, x to the 8th behaves like this, but that's not what we have. What we have is okay, that's a correct statement. So x to the 8th behaves like this. That's a true statement, but the question is not x to the 8th. The question is, how does x to the 5th minus root 5 times x to the 8th plus root 2 times x to the 4th minus 12 behave in the extremely large positive and negative x values? So what is the end value, the end behavior of q of x? Q of x behaves not like x to the 8th, it behaves like negative root 5 times x to the 8th. Well, negative root 5 times x to the 8th is a stretched vertical reflection of x to the 8th. So instead of up, up, we know we've got down, down. And that's how q of x is going to behave. So perfect, we got it. So it's kind of similar process here. Let's just call this one r of x. And maybe let's knock off the monkey business. Let's just write it in standard form to begin with, just to save you a little bit of hassle this time. I've already reminded you like twice to pay attention to that. So, okay. This time it's already in standard form. So what's the end behavior? So we figure out how does x to the 7th behave, and then stretch and or flip it as necessary depending on what's the coefficient, and then we get the final answer. So find the leading term. So it's negative 1/2 times x to the 7th. X to the 7th behaves like x cubed. We multiply x by itself 7 times. We get a positive number to the 7th power is positive. A negative number to the 7th power is negative because the one left over. But we don't have, we're more interested in the negative of that. So negative 1/2 times that is, it's half as big, but it's still going to infinity. But then we also multiply by a minus sign, which means it doesn't go up anymore, it goes down. And then for negative x's, that one you also do the opposite. And we know that same end behavior, that's it. So what happens in the middle, who knows? Lots of interesting things might happen. But for extremely large x's, extremely large positive x, extremely large negative x, we've got this and we've got that. And that's it. I think that you should be in pretty good shape here. Let me do one. Let me do one that's a little bit, let's make it a little bit more interesting. I'm gonna make room for one more here. Sorry, I don't, this is a very reasonable question that maybe it could come up later. You'll just, look at the homework, look at the practice test, see if there's one like this. This is pretty reasonable. This next one is slightly harder, but it's okay. There's just a little bit of algebra, that's all. F of x equals 2 minus x squared times x plus 3. Okay. I could include even more if I wanted to, but let's not. Let's just multiply this out. So we get 2x plus 6 minus the middle ones. And then minus 3x squared. Okay, so that's it. That's all the algebra for this one. If I wanted this to be a longer problem, maybe there would be 3 of them. But here's what's important. There's our leading term. So I'm asking to find the end behavior. Why did I multiply this out? Because now I know what the leading coefficient is. X cubed behaves like this. But what we don't have is not that. We've got -1. Our leading coefficient is -1. And we have so it's okay to include this as a part of your work, but make sure it's very, very clear that your final answer is that's the end behavior of x cubed. That's the end behavior of -x cubed. Same end behavior as this one is called f. So this one right here. There we go. So that's one where there's an extra algebra step. It's a little bit conceptual. You have to recognize that, sure, I can figure out what the standard form of that is. And some of the even trickier ones might be like, if you can figure out what the degree is going to be and whether the leading coefficient is positive or negative, then a lot of this other stuff is just details. That's going a little bit it's going a little bit farther than we need to. If you understand this one completely, then you basically understand everything you need to here. So that's it. So all right, have fun with those.